Okay. Yes. Oke. Pak Adit sudah siap? Pak yang bagian apa spotlight Pak Adit ya?
Oke, Pak.
Ya, sama yang lainnya. Oke. Professor Nicola, we can start. Yeah. We can start. Yeah.
I am ready.
Okay. Okay. Yeah. Hello everyone. I am Editri Baskoro, the host of the Combinatoric Today series. Good afternoon, good evening, and also good morning to all of you in the various time zones. Welcome again to the Combinatoric Today series, and it's our pleasure for us to see you again in this wonderful occasion. And I should mention that today is going to be the 13th edition of the series in this second year. First of all, I would like to thank the Faculty of Mathematics and Natural Sciences for the continuous support and the encouragement in conducting this event. I'm privately very happy that through this series, we could invite prominent combinatorists from various countries all over the world to present the current and update development of our below fields, which are combinatoric and graph theory. Today, we have a very special speaker. Please have a big welcome to Professor Nicolas Trotignon. He's a professor at the CNRS, lives École Normale Supérieure de Lyon. Hello, Professor Nicolas. How are you today?
Hello, thank you. I'm fine. It's 8 o'clock in the morning in Lyon. It's a perfect time to start a good day.
I'm really sorry to beg you to give mathematics lectures today in this early morning. I think over there, what time is it? It's 8 o'clock, right?
It is 8 o'clock in France, yes.
Okay, so thank you for your kindness and willingness to deliver a lecture in this series. And we are very happy to have you here. And your lecture will be chaired by Dr. Joko Supriyanto. And we would like to mention here that this program is brought by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, with collaboration with the Center for Research Collaboration on Graph Theory and Combinatorics, Indonesia. Before I let Pak Joko to chair the lecture, let us have a group photo. Please, Pak Adit, please have us.
Okay, thank you. So I would like to invite everyone to turn on their camera so we can take a group photo together. Maybe I'll wait for a few seconds. If you want to join in, please turn on your camera. Okay, I'll count down from 5, 4, 3, 2, 1. Okay, one more. 5, 4, 3, 2, 1. Okay, thank you, everyone.
Okay, thank you, Adit. And now I ask Dr. Joko to share the lecture.
Okay. Thank you, Pak Edi. I will try to share a short file regarding the curriculum vitae of Professor Nicolas. Hello, hello everybody. Welcome back to our Combinatorics Today series. I will introduce first the curriculum vitae of our guest lecturer, Professor Nicolas Trotignon. I'm so sorry for my maybe mistake pronunciation because I know nothing about French. Okay, Professor Trotignon, perhaps this is a kind of bachelor degree in statistics and economy in 1995, and then he obtained this perhaps a kind of special in French and educational system in French. He obtained or he followed aggregation de mathematics in 1997. This is a French competitive exam for teachers in high school and universities. And after finishing his master program in operation research and combinatorics in Joseph Fouillé University in 2001, under the supervision of Sylvain Grevier, he obtained his PhD in mathematics and computer science, also from the same university in 2004, under the supervision of Professor Frédéric Mavray. And in the next 5 years, he wrote his habilitation thesis entitled Structure of Classes of Graph Defined by Forbidding Induced Subgraph in another university, in the University Paris Diderot, Paris 7, in Paris, in French, 2005, 2009, I mean, sorry. And this is regarding his research and scholarly experience. In 2005 until 2008, Professor Trotignon became an assistant professor in the Université Panthéon-Sorbonne, Paris 1. And then from the next 3 years, he becomes a researcher at the CNRS, still the same university, or I think different university. And then from 2011 until 2015, he becomes a junior researcher at CNRS, École Normale Supérieure de Lyon, French. And from 2015 up to present, he is a senior researcher at the same university. And now, still, regarding his research and scholarly experience, I have to mention that Professor Nicolas Trotignon has published over 50 articles, scientific articles, and has supervised 3 postdoctoral students and 6 PhD students, including David, I think, and over 10 master students. And he also became a referee for many mathematics and computer science journals, and among them including several known very high standard journals, like Journal of Combinatorial Theory, Series B, Journal of Graph Theory, Discrete Mathematics, Discrete Applied Mathematics, and also Applicable Analysis and Discrete Mathematics. And for today, he will give a lecture about the structural graph theory. The exact title of his talk is With an Even Whole Free Graph, a tour in structural graph theory. So let us invite Professor Nicolas Trotignon to give a talk. So please, Nicolas, the time is yours.
So thank you very much for the introduction. I'm gonna share my screen so that you see my slide. Let me see. It should be fine like that. So tell me if you are happy with what you see.
Yes, perfect.
So, so let me check the time. Okay. So I'm gonna talk about widths and even whole free graph. So just for a super short introduction, everything will be defined later in the talk. But even whole free graph are a very specific, is a very specific class of graph. So something a bit specialized, but I think it's a good, having a look at them is a good way to see more general stuff in structural graph theory. And I try to convince you about that. So first, okay. First, I will talk. I will present what are even whole free graph. So first, a hole in a graph is a chordless cycle of length at least 4. So it's a cycle. I think the basic knowledge of graph theory is known by everyone, but do not hesitate to interrupt me. So you have here example of holes that are drawn, and it is important that you don't have a chord in your cycle, and the chord is the red edge on the last example. So the last example that I've drawn is not a hole because you have this extra edge. It contains a hole, but it is not a hole. Okay, and the hole is odd or even according to the parity of its length. And the length is the number of vertices or edges. It is equivalent for a cycle. Okay. And as we will do throughout all the talk, we will many often define graph by excluding something. And the first example is a definition. A graph is chordal if it has no hole at all. And there is a super classical theorem. It is from the 60s. Sometime it is, well, it is almost folk. Maybe Golay or Dirac prove it first. That chordal graphs are exactly the graph obtained from complete graph by repeatedly gluing along cliques. Is a clique, is there a need to define what is a clique? Set of pairwise adjacent vertices. Maybe I can try to test my webcam. Let me see. You see, if I switch to this, normally you don't see my picture anymore, but you see a piece of paper on my end drawing. Yeah. So I will draw you an example of a chordal graph. You see, I start with a complete graph. Then I glue along cliques a previously constructed chordal graph. So chordal graphs, they really look like that. And you don't have holes in them. They are kind of trees of cliques, like that. See, and until the theorems, it is the only way that you can have a chordal graph. You may glue along an empty clique, of course. There is no need to say that the graph is connected. This is a chordal graph, and you glue these two along something empty. Okay. So now I can go back to my webcam. Okay. So a bit of history. The word hole was popularized by Claude Berge in the 60s, and because of a particular conjecture. He says that Claude Berge conjectured that for every graph G, if G has no odd hole and its complement has no odd hole, then you have the equality between two parameters of the graph that are chi of G and omega of G. And chi of G is the famous chromatic number, and omega of G is the size of a maximum clique in G. And of course, these parameters are kind of dual, because you have a trivial inequality that chi of G must be at least omega of G. Why is that? Because when you have pairwise adjacent vertices in a graph, say you have 5 pairwise adjacent vertices, of course, to color them, you need 5 colors because they are pairwise adjacent. So each of them needs its own color. So chi of G is at most omega of G, and the converse inequality is false in general. Here I've drawn you a graph on the screen that has 5 vertices. I'm sorry, I cannot see the graph myself. Okay. Here, the graph that you've seen has 5 vertices, and to color it, of course, you need 3 colors because it is odd. I think all of you know that. But you may notice that omega of G, the maximum clique in G is 2. So you have chi equals 3, omega equals 2, you don't have equality. And this graph is in itself an odd hole. And so Claude Berge made this conjecture that in some sense, this is the only counterexample you have to chi equals omega. So in the sense of this conjecture, and this was known as a strong perfect graph conjecture. So I write it again. For every graph in G, if G contains no odd hole, also you need to exclude odd hole in the complement. I will not explain this. This is not the main focus of the talk, but you really need to exclude this. Then chi of G equals omega of G, and this was a strong perfect graph conjecture. It was one of the most famous open question in graph theory until it was proved in 2002 by a group of 4 researchers: Trotignon, Robertson, Seymour, and Thomas. So you see that, and this conjecture has a lot of, these graphs where chi is equal to omega are very important for linear programming, for a lot of things. So it was an important problem in graph theory. So how this conjecture was proved? So this group of researchers, they had a structural graph theoretical approach that I explained you. They proved that for every graph G, if G and its complement contains no odd hole, chi of G equals omega of G. So this is just a rephrasing of the conjecture. And a graph such that you don't have this odd hole is called a Berge graph. And to prove the conjecture, they proved the decomposition theorem for Berge graphs. They prove that every Berge graph in G is either basic in some super well understood class or has a decomposition, so a kind of a divide and conquer approach, that if the graph is in your class, then either it is simple or you can cut it into pieces. So just like that, it looks simple. But of course, the decomposition theorem is very long to state. I think if you want to state it in the paper, it takes maybe 2 pages to state it, including the definition. So we will go through this later in the talk. But also it is super long to prove. The proof takes something like 150 pages. So it is something very complex, this decomposition theorem. But once you have it, the proof that it implies that chi is equal to omega is something rather simple. You need maybe something like 4 or 5 pages of nice argument and coloring, and you prove that you have chi equals omega. So the big stuff is the decomposition theorem. This is where is the difficulty. And so such a thing, even a super good researcher like Trotignon, Seymour, Robertson, and Thomas, if you give them the problem, they don't sit and immediately come with a statement of the decomposition theorem. It is a long history of many researchers that led to the right structural conjecture that was proved by this group of researchers. And in this history, even whole free graph played a very important role. They were used at some point as a prototype of Berge graph for several reasons. First, they are similar because you exclude holes of some parity. So in both classes, you exclude holes with parity, so they share something in common. They are similar. The second reason is that they are different, because if they were just the same, they would not be a good prototype. They need to be simpler so that you experiment ideas, techniques on them. And in what sense they are simpler? I think there are 2 main reasons why they are simpler. They are simpler because they are square-free. The square is the whole on 4 vertices, and excluding it really helps a lot. You don't have a complete bipartite graph, for instance, when you exclude a square. The square are a bit everywhere. You don't have twins, you don't have 2 vertices non-adjacent with the same neighborhood, because then this would imply a square. It gives you a lot of structural information that you don't have in perfect graph. And they are also simpler because even structures are everywhere, which is not the case of odd structures. And let me explain this. So I switch to my camera. I switch to my, oh, okay. So normally you see my piece of paper. And if I draw you two vertices like that, and a lot of different paths linking them, suppose you have this in a graph. Then you have a super simple pigeonhole principle application. These paths, if you have many paths, some of them must have the same parity. You have only two parity on Earth, odd or even. So if you have three paths, two of them have the same parity. And so the cycle, let us call epsilon this parity. The parity is epsilon plus epsilon. It is even. If epsilon is even, it is, or if it is odd, epsilon plus epsilon is even. So parity is everywhere, and odd is not everywhere. It might happen that all the paths are even, for instance, even if you have billion of paths, and then every cycle you can have is even. You don't have an odd cycle. So, of course, here I talk about cycle, not about holes, because you might have a lot of chords everywhere, and it does not mean that you have an odd hole. You have an even hole. You just have an even cycle, but still, as we will see later in the talk, it is very difficult to draw a kind of complicated generic graph that has no even hole. If you study even hole free graph, you can study them quite long and believe it is a trivial class that has nothing in it, which is really far from truth, but it is something you can believe because of such kind of stuff. Also, I can give you, so I switch back to my main webcam. Okay. And I tell you a trivial theorem. Every even hole free graph, I will write EHF for even hole free. Every even hole free graph that is bipartite is a forest. Because if your graph is even hole free, and you take a shortest cycle in it, this shortest cycle cannot be even, it must be odd. It can, yes, what I say, it is even hole free. So a shortest cycle cannot be odd because it is bipartite. It cannot be even because it is even hole free. So in fact, you have no cycle, so it is a forest. So bipartite graph in even hole free graph are super simple to understand. It's just a little remark to say that they are simple. If you exclude odd holes, you don't have such a simple characterization. Every bipartite graph is odd hole free. Okay, and this idea of taking even hole free graph as a prototype for Berge graph was super successful because in 1997, a group of researchers, so Michele Conforti, Gérard Cornuet-Jols, Ajay Kapoor, and Kristina Vuskovic, proved a decomposition theorem for even hole free graph. There is now a more recent and stronger theorem. I will not give the detail. But in 2001, using the same technique, the same group of researchers proved a decomposition theorem for square-free Berge graph. And they made in this paper, they made the right conjecture that was proved by the group of researchers I mentioned already, and that led to the proof of the strong perfect graph conjecture. So it is not just a little idea like that even hole free graph are a prototype for perfect graph or Berge graph. It is really what happened in the history of how the paper were written and how the idea was found. So now I'm gonna give more details about the comparison between Berge graph and even hole free graph. So I told you that in both cases you have a decomposition theorem. So you have a theorem saying that your graph is basic or has a decomposition. So what are the basic graph in both cases? So for Berge graph, here is the list of basic graph. Bipartite graph, their complement, their line graph. Is there a need that I define a line graph? The line graph of a graph is something you obtain. You take a graph and you will consider its edges as object that will be the vertex of the line graph. And two such vertices that correspond to edges in the original graph, they will be adjacent if the two edges share a vertices, if they are incident at a vertex. So you take bipartite graph, the line graph, the complement of the line graph, the complement of the line graph. So all this is a bit complicated to see, but it is a list of basic graph. And for even whole tree graph, the basic graph are complete graph and graphs that are formed by the line graph of a tree plus two vertices. These are the basic even whole tree graph. So you see the two lists, if you compare them in a structural point of view, it is really far much complex for Berge graph, because bipartite graph, you have a lot of freedom to build a bipartite graph. It can be anything, any bipartite graph, while the line graph of a tree is something much simpler. It is something kind of trivial in some sense. And the complete graph is super trivial to understand, of course. Now the decomposition. So there is one decomposition that is common to both classes of graph, and this is called the two-join. It means that you partition your graph into x1 and x2, and between x1 and x2, the edges you have are only the edges that cross from A1 to A2 and from B1 to B2. And I've drawn this little cross to insist that you have all edges between A1 and A2 and all edges between B1 and B2. And then when you have such a decomposition, it is very good for algorithm because you can simplify one of the sides as I drawn and recurse an algorithm, etc. I would call this a good decomposition, something you are happy to find in a graph. And you have a lot of papers about two-join that you can detect them in polytime. And when you can decompose recursively with them, you can do a lot of things like computing stable set, etc. All this is a bit complex, but nice. There is one decomposition that you have only in Berge graph. So two-join in the complement homogeneous pair, I don't, you might call these details because you have stronger version of the theorem when you can exclude them and you can handle them. So I don't spend time on them. And there is one that is kind of common to both classes. This is called the skew partition. So in a Berge graph, a skew partition is you partition your vertex set into 4 sets, and between the 2 sets that here up and down, you have all possible edges, and between the set L and the set on the left and the set on the right, you have no edges at all. This is called a skew partition in a graph. And in even whole tree graph, you only have particular skew partition because you might notice that if on the top set you have 2 non-adjacent vertices and on the bottom set you have 2 non-adjacent vertices, this will create a cycle of length 4, and you don't have this in an even whole tree graph. So in fact, in an even whole tree graph, you have the same decomposition, but because the graph is even whole tree, it is kind of degenerate, and one of the box is made of 1 vertex. So the decomposition is a bit simplified. And this decomposition is kind of the bad guy. I mean, it is very difficult to detect in polytime. So you can do it, but really it was for a long time an open question, and it is difficult. And also, what can we say is that if a graph has this decomposition, even in quite a strong sense that you have it in every induced subgraph, for instance, it is very hard to use in algorithm. It is notoriously hard to design algorithms that make use of the presence of this decomposition. And it is a kind of, I think if you would explain graph theory to people in another planet where people did not discover a perfect graph, I would be very surprised that they found a use for this kind of decomposition. To my knowledge, it is useful only in a perfect graph. It is very hard to to use this decomposition if it is not in the context of perfect graph. So here is a picture. And then when you see this, you might wonder, are even whole free graph nothing? Why is this question? Because the decomposition that you have are really less than these in Berge graph. And it is hard to, I say this already, it is hard to draw on board a generic, complicated, even whole free graph. So we will talk about this later in the talk. And also there is a very strange fact that for Berge graph, there are several problems that you can solve in polytime, and most notably coloring and maximum stable set. This is a famous theorem by Grütschel, Lovas, and Schreiber from the 80s. These algorithms are not combinatorial. They rely neither on the decomposition theorem or on structural graph theory. They rely more on the property of mathematical programming, linear programming, etc. And in contrast, for even whole free graphs that are much simpler structurally, the problem of coloring and maximal stable set are both open. It is not known if it is polynomial time or NP complete, or maybe somewhere in between. This is not known. I would say something stronger. I mentioned chordal graphs that have no hole at all. So chordal graphs are in fact the intersection of even whole free graph and Berge graph. They are really the intersection of both class. And there is not a single problem that is known to be polynomial solvable for chordal graph and NP hard for even whole free graph. So even whole free graph are a generalization of chordal graph. It is a superclass of them, but in the sense of solving problem, it could be that the two classes are kind of equivalent, even with a super artificial problem that will be designed only for this purpose. I am not aware of something that is NP hard for even whole free and polytime for chordal. So really there is a question with this even whole free graph, what are there? And it is, I ask the question, are even whole free graph nothing? Or maybe I should say nothing more than chordal graph. And the answer is no. Really there are now evidence. In the rest of the talk, I will tell this evidence that even whole free graphs are not nothing. They are complex, and studying their structure is still interesting today. So I'm going to talk you now about weeds. So I think weeds, if you had to spend to design a course for students, maybe in a master, and you want to give them something about structural graph theory, you should definitely teach what are these weeds. It is something important and something generic, because in this all this structural graph theory, sometimes you have the feeling that you study one class after another, and you don't see a direction. You can always define a new class by excluding this graph or that graph, and it can go forever. But weeds are something good because they give a meta theorem. All these graphs are simple in some sense. All these are complex in some sense. So it is something good to know. And so a weed is something that measures how complex is a graph. But of course, you have many ways to define the complexity of a graph. You have many weeds, and the most famous notion of weeds is the tree weeds. So here is a very short definition of the tree weeds of a graph. It is not the most famous definition, but it is the simplest to give, the shortest, and it has also the advantage to play a role to chordal graph, and which is good in this talk since chordal graphs are defined by excluding holes. So it makes a kind of a bridge between all these classes of graph and the notion of tree weeds. So the tree weeds of a graph is the minimal omega of h. I remind you that omega of h is the size of a maximum clique. So you have a technical -1. So it is a minimal omega of h where h is is a chordal graph that you obtain from G by adding edges. So if you take a graph G and you add all possible edges, what you obtain is a complete graph. And the complete graph has no hole, because every cycle you draw, apart from a triangle, will have a chord since you have all possible edges. So when I give you a graph, it is always possible to make it chordal by adding edges. And a simple recipe is add all possible edges. But of course, maybe you can put less edges to have it chordal. And if your goal is to not to have a too big clique, it is quite complicated to do this structurally. And the minimal way to do it will give you the tree width of the graph. And the tree width will tell you how far your graph is from a tree. If your graph is a tree, you have nothing to do. Your graph is chordal, there is no cycle in it. And the tree width will be the maximum omega of G, and omega of G is 1. There is no triangle in a tree, and your tree width will be 1. If it is a tree, it is 1. And trees are exactly the graph where it is 1. And then the tree width, if the tree width is 2, you will have the famous class of series parallel graph that are kind of a tree that looks a bit like a tree in some sense, because these series parallel graph are kind of cycle glued in a tree fashion. And after, when the tree width becomes bigger, it is hard to figure out what it is, but it is a kind of a measure of how far from a tree you are. You have the notion of rank width. So I will not, I write you the definition. I will not go through it because I will run out of time and cannot say what I plan at the end of the talk. So just remember that the rank width is a generalization of the tree width, in the sense that if you have a class of graph with bounded tree widths, then it has also bounded rank width. And the rank width is a generalization of the tree width where a complete graph has a small rank width. Complete graph has a big tree width, but they have a small rank. They are simple in some sense, complete graph. So it is a generalization of the tree width that captures the idea that a complete graph has a small rank width. I think a rank width was defined by Sangil that gave a talk in your series, no? Maybe he defined it during his talk, I don't know. Because it was one of his main results during his PhD, I think, was the definition of the notion of rank width.
Okay.
So why are we interested in widths? Mostly for algorithm, because of algorithm, because if you have a class of graph with some bounded widths, then you can solve, there are generic methods that tell you that if the width is bounded, then you have a polytime algorithm for many problems that you can define in some logical language, like a monadic second order logic, and in particular, chromatic number and alpha. Also, you might notice that bipartite graphs are very simple regarding chi and alpha. Coloring a bipartite graph is trivial. Computing a maximum stable set in a bipartite graph is not that trivial, but doable. And but they have unbounded widths. The bipartite graph, regarding the widths of graphs, they are super general. So Berge graphs are a bit strange, because the basic graph in them, like bipartite graph, are very simple regarding some specific algorithm, but super complex regarding widths. They have structurally, they are super generic bipartite graph. So this notion of widths are kind of useless to study perfect graph, to my knowledge. I am not aware of a single interesting theorem about perfect graph and their widths. Okay, but for even whole free graph, there is a lot of hope, because you don't have this problem of bipartite graph sitting in the class and having a super complex structure. So if you take a big picture, you can say that Berge graph or perfect graph equivalently are simple regarding some algorithm and super complex regarding their structure, while even whole free graphs that are very similar, they are potentially very simple regarding their structure, and regarding algorithms, the problems are open. So the picture is a bit strange. The class that is more simple structurally or potentially more simple, is much more complex regarding algorithms. This is very strange. But of course, the problem with even whole free graph is that in fact, structurally, they are not that simple. They are not that simple. And I will go, because how to say this? They are not that simple, but it is not very easy to, it is not very easy to exhibit graph of complete widths and of unbounded widths. And I will tell you about that. So a first example of even whole free graph are complete graph, and they have unbounded tree widths, but as I told you already, they have bounded rank widths. Also, there is another generic example of graph with unbounded widths, and they are chordal graphs that we talked about at the start of the talk. Chordal graph, in fact, they have unbounded widths, whatever notion of width you take. So then you might say, okay, I cheated you a little bit. I told you that even whole free graph are structurally potentially simple, and then I tell you that chordal graph have unbounded widths. But in fact, I think this is an illusion, because chordal graph, as I told you, you can draw them by gluing along cliques. And so every chordal graph is decomposable. Either it is a complete graph or it has a clique separator. And clique separator, they are super good for some structural purpose. First, you quite understand what you do when you glue along a clique. And also to compute chi and alpha, they are very easy to use, this operation of gluing along a clique. So in fact, when I told you about the structural complexity of a class, I assume that when I glue along a clique, it is simple. So I will focus only on even whole free graph that has no clique separator. And since I will talk about them a lot, I give them a short name, EHF NCS. It means even whole free, no clique separator. So if I focus on these graphs that are really the graphs that annoys me when I want to do algorithm, if I focus on these, then it starts to be really non-trivial to draw some that are complex. I promise that if I take 100 graph theorists and I ask to all of them, give me a super complex graph, complex in the sense of your experience of graph theory, and that has no clique separator, I bet you that 99 of them, or maybe all of them, there will be an even whole in their graph. You really have to fight hard to draw something a bit complex that do not contain this even whole. So I will now give you what I call positive result and negative result. So positive result, what are they? They are results telling you, oh, these even whole free graphs, they have bounded widths. And negative results will be, no, I can draw some of unbounded widths. So positive results, planar graph. It is a theorem by Silva, Da Silva, and Sales, a researcher in Brazil. They proved that planar graphs that are even whole free with no clique separator, they have bounded tree widths. Also, triangle free and cap free. A cap, it is a whole plus a triangle. So if you exclude these, or just exclude triangle, then Cameron, Da Silva, Huang, and Vushkovich proved that the rank width is bounded. And if you exclude just triangle, in fact, the tree width is bounded. Also, if you exclude a pan is a whole plus one vertex with a unique neighbor in the whole. If you exclude this in this class of even whole, no clique separator, then the rank width is bounded. Also, if you remember star cut set, we define them. It is a cut set in the graph made of one vertex plus its neighbor. If I give you an even whole free graph with no star cut set, then Hang Le, he was my PhD student, he proves that the rank width is at most 3. And the proof is by decomposing along the two joints that we've seen already. Okay, so with this result, you have a new proof of the fact that you can color even whole free graph with no star-cut set. And it was something that I proved with a more specialized proof with Kristina Vuskovic. And you have a similar algorithm for Berge graph. Okay. So with all these positive results, if you spend some time thinking about them, you might believe that really there is something to do in general with even whole free graph and weeds. But I'm going to show you that it is not the case. So first, we want even whole free complicated graph. And because of all the sketch that I made you about the positive result, you know that they must contain triangle, caps, bands or large clique and star-cut set. So I will give you the first attempt. So Golombek and Rotix gave example of chordal graph of large rank widths. So the main ingredient for this is this graph. So you see this graph, you should see the vertical set, the two vertical set as cliques. And you see that you have big vertices on the bottom, and each vertex, when you grow in the graph from bottom to top, each vertex is losing a neighbor. This is sometimes called the half graph. The graph with this particular structure, it is a chordal graph. This graph has super small rank widths, but if you take a chain of them, then suddenly you have a large rank width. You might notice that it is wrong. It is not what I want because it has a clique cut set. Remember that these vertical set are cliques. I didn't draw the edges because then you would see nothing. But these cliques are a clique cut. If you remove one, you disconnect the graph. But then my PhD student, Hongler, has just a super simple idea. Just to identify the left click and the right click, you make them into a circle. And then you have an even whole free graph. You don't have any more a click cut. And the rank width is unbounded. I think it was in 2017, so long after all the history of even whole free graph, but it was the first example ever of an even whole free graph of large rank width, no click cut. It was not known before that, even if it is very simple. Then later, with several co-authors, Isolde Adler, Heiko Müller, Marko Radovanovic, and Kristina Vuskovic, we provided examples that are diamond-free also, which are more complex. I don't spend time on this example. And with my PhD student Dewi Sintiari, that most of you know, I guess, because she came from Indonesia to do her PhD in France, we gave an example of even whole free graph of large rank widths that is K for free. And the construction is really complex. I will have no time to define you all the construction. It was really a complex construction, and for most researchers of the field, it was a surprise because it was conjectured by Qin Huang and Kathy Cameron. It was conjecture that in fact the rank width and even the tree width should be bounded if you exclude K4. But you can build a K4 free graph by a complex recursive construction that are even whole free and have no click cut. So I sketch you a step of the construction. And this construction, in fact, contains even hole. You have to tune it again to kill the even holes by introducing triangle in it. All this is a bit complex. So, I will make a conclusion of this part of the talk. What I would like to say is that the structure of even whole free graph is still far from being understood. You have this strange graph sitting in the class, and I think it is a nice specialized subject in graph theory. And there's a lot to do again about their width and the structure. So now I would like to talk to you about something related to this, but a bit different. It was a great surprise for me and Dewi to realize that all the work that we did has an impact outside of the super specialized community of people studying decomposition theorem for classes of graph. And I will explain this to you. The title of this section is Graph Minors, because it refers to the series of papers on graph minors made by Robertson and Seymour. This is maybe the most important work in graph theory, say in the last 40, 50 years. Neil Robertson and Paul Seymour gave a generic way of describe classes of graphs that are closed undertaking minor. So maybe I should, we don't really need the definition, but a minor of a graph is a subgraph that you obtain by removing vertices, contract edges, and delete edges. And Robertson and one of the many important theorems that Robertson and Seymour proved in their series of papers is the following. It is the fact that there exist functions such that any graph of trioids, of huge trioids, at least f of k, must contain a wall, well, a grid or a wall. On the left, I've drawn a grid. On the right, I've drawn a wall. Must contain this as a minor. So it is not that it contains a wall or a grid. I mean, you have a correct theorem if you write grid, and you have a correct theorem if you write wall. Both are equivalent, because since you look at it as a minor, by contracting edges in a wall, you obtain a grid. And by removing edges in a grid, you obtain a wall. So containing one or the other, if you don't care for the exact size, and since you have a function in the theorem, you don't, it is equivalent to say a grid or a wall. So people, I think most of the time people say wall, because it is just easier to draw a wall when you give a talk on the board. But when you work with induced subgraph, you always say a wall, because it is true that a grid contains a wall as an induced subgraph. You can ignore vertices and draw your wall, but it is not no more true that a wall contains a grid as an induced subgraph. So people from induced subgraph, it is not at all equivalent for them, and from far they prefer the wall. Okay, so I will only use wall later, but this theorem is called the grid theorem. And the grid theorem, it would be, from the start of the talk, I only use the notion of induced subgraph. And this grid theorem is wonderful because it certifies you that it gives you a certificate for a graph to have large trioids. A grid has large trioids, but it is an if and only if statement in some sense. If your trioid is big, you have a wall in your graph. So, and you have it as a minor. It would be wonderful to have it as an induced subgraph. It would give you much more information. So let us dream a bit. Is there an induced subgraph version of this where you replace minor by induced subgraph? And of course, the answer is no. It is immediately is no. But why is that? A first counterexample is a complete graph. A complete graph has large trioids and does not contain a wall as an induced subgraph, obviously. So the guess was wrong, but maybe you can say, maybe the theorem is more complex. You will say, oh, if I have a large trioids, maybe I have a clique, maybe I have a wall, and it would still be a nice theorem. But no, false. There is another counterexample, which is the complete bipartite graph. The complete bipartite graph does not contain a wall as an induced subgraph. It is very easy to check. So you should add it to your potential theorem. There is another, of course, you have the wall, but the wall you need to be careful. When you do induced subgraph, it might happen that your wall is subdivided. Subdivided, it means that you add edges you add vertices in the middle of edges. So if you subdivide your wall, the trioid is still big, and you do not contain the wall as an induced subgraph. If you remove vertices, you will never obtain a wall. So you need to add to your theorem wall subdivided. And also something a bit weird, you have to add the line graph of a subdivided wall. And this is what I've drawn on the right. It is just your wall, but at every vertex where you branch, you put a triangle. Because this, of course, it contains a wall as a minor, because you just have to remove one edge in every triangle and you obtain what you had on left. But if you do induced subgraph, you are not allowed to remove edges. So you're stuck when you branch, you have to have the triangle. You might say, oh, maybe I have a combination of the wall and the line graph of a wall. It means sometimes I have hubs that are vertices, and sometimes I have triangle. I could make a mixture of them. But then if you make the mixture of them, by some Ramsey argument, if it is huge, you can extract either the left part or the right part from it. So you don't have to consider the mixture of them in your theorem. You don't have to. And then I think Zdeněk Dvořák was maybe the first to ask the question. He says, maybe there is a theorem there. It would be wonderful that a graph has a large tree width if and only if it contains one of these big substructure. But then, in fact, the construction that we made with Dewey kills this conjecture. We didn't do it in this purpose, but it turns out that it kills this conjecture because what we have is an even whole free graph with no K4 and high tree width. And it is very easily seen to be a counterexample because you might notice that our graph has no K4, so it has no KL, it has no big KL. It is even whole free, so it has no complete bipartite graph. And you can, I told you at the beginning of the talk, even structures are everywhere. If you have a big wall or a big line graph of a wall, then you must have an even whole. It is mandatory because for the argument I gave you, you take two hub vertices far away and you have three disjoint paths that link them. And by a simple pigeonhole principle, two of the paths have the same parity, you have an even whole. Even by subdividing in a very clever way, you will never kill even whole in this. So our construction is a counter example to this. So now Dewey and I, and also several researchers start to think, okay, we have a counterexample. We have so what do we have? We have a graph of large tree width and no L obstruction. What is an L obstruction? It is what you had in the list of Dvořák. Cliques, complete bipartite graph, walls, line graph of wall. Just for short, we call this the L obstruction, simple obstruction. So to have a large tree width and no L obstruction, our construction with Dewey needed a large clique minor. Our construction has big tree widths because of a large clique minor, okay? It has a vertex of large degree. It had a huge number of vertices. To reach some tree width K, we need something like 3 to the K vertices. So to have a counterexample, we need many vertices. We need to be rich in vertices at least. And we have a wheel. A wheel is a particular induced subgraph that I don't define here. And we were wondering, maybe we have a weakening of the question of Dvořák by saying that these are mandatory. And then if we reverse, we have, a graph with no large clique minor, then the picture is as we believe initially. So because of this 4 bullet, we have 4 conjectures. And it is it was really a surprise to me that when you make these big conjectures, sometimes they stay open for years and years. But in the 2 years after we made these 4 conjectures, they were all proved or disproved. So really there was a very big interest in these, and as you will see, everything is proved, and I will survey this. So the first that was proved, in fact, it was with Pierre Aboulker, Isolde Adler, and Yeon-Jung Kim. Dewey and I, we could prove that if you have no L obstruction and no KL as a minor, in fact, the tree width is bounded. So really, what we did in our construction is mandatory. You really need to have a big click minor in your construction. So seemingly, this was known from the community as a consequence of big theorem in graph minor theory, but no one, even as a conjecture, we really search all the BIB. It was written nowhere, even as a question, as a conjecture. And we could prove this from a theorem for obstruction to triwids by construction by Fomin, Golovac, and Tilikos. Okay, so first bullet done. The intuition was true. You really need a big click minor. Second observation, you need a lot of vertices to bound the triwid. So if you reverse this notion of lot of vertices, you might believe that this is really needed to have a lot of vertices. And if you reverse this, you say, okay, if I don't have this obstruction, then the triwid is at most the logarithm of the number of vertices. And this would be super interesting because many problems, I told you that if the triwid is bounded, there are many algorithms for several problems. And it turns out that in many cases, the complexity of the algorithm is 2 to the triwids. So if the triwids, if the logarithm of the number of vertices, 2 to the triwids become linear, become just the number of vertices. And so this logarithmic conjecture was proved by Tara Abrishami, Maria Chudnovsky, Seper Rajebi, and Sophie Spirkel. They could prove it in a particular case where you exclude some substructures that I don't define. Also, it was proved by a long list of researchers that are all French, except for Alexandra Vecholek, in several particular cases, but it was disproved in general. There is a counterexample found by James Davis this year. And I told you that there was a conjecture about being wheel-free, but the construction of James Davis is wheel-free. So with this construction, he killed 2 of the 4 bullets. And there is one last bullet that was open. It is when the degree is bounded. But this was proved by Tuka Korhonen, who is a PhD student in Bergen in Norway. He proved that if you bound the degree of a graph and the triwids is big, then you must contain a KK grid as an induced minor. An induced minor is something you obtain by deleting vertices and contracting edges. And as a corollary, you obtain that if you exclude L obstructions and the max degree of the graph is bounded, then the triwids is bounded. So this is a very nice general result that was proved recently and suggested by the construction we did with Teori. So I think I'm done. I told you what I wanted. And there is time for questions. And maybe Eddie told me that there is maybe a break between my talk and questions. And we don't hear you.
Okay. Okay, thank you, Professor Trotignon. So now we are entering the question and answer session, but before there will be an art performance videos from Paddy. Okay. So yeah. Please, Paddy.
Yeah, okay, thank you, Pak Joko. So I would like to present you some cultural instrument from Indonesia. So just let me share with you my song. Just a moment. Okay. Cultural music. Yeah. Okay. Yeah. Let me, you are. So yeah, we will having some angklung performance. Probably you know Professor Nicolas. So angklung instrument is made from bamboo, traditional musical instrument from Indonesia, from Sundanese culture. Okay, and the title of the song is Viva da Vida. Yeah, enjoy.
When I gave the word, now in the morning I sleep.
Okay. This moment. Yeah. I hope you enjoy Professor Nicola.
Yeah, thank you.
This recording actually recorded by a student during pandemic.
Ah, okay.
Yeah. So nowadays we can use our mobile to play the instrument.
And what is the name of the instrument?
Angklung.
Can you write it
Uh,
in the chat? So,
okay, I will write it. Yes.
Okay, now I invite all of you, all the participants, to give a comment or the questions, please. Bu Hilda or Bu Rino, maybe? Are there any questions or comment from Vanida? Do you have any comment or questions? Professor Vanida?
Can I have one just for to the future the direction? So
Okay.
Professor
Please,
Nicola, I think the lecture that you are given today is very interesting and also very hard for us. Not many people in Indonesia are still mastering this topic, and we would like to know the future direction to in this field, in this structural graph theory fields. What kind of problems that's very I mean important and interesting to work on.
yes. So it's not a very easy question because it's hard to predict. Maybe I will sit on a problem, and even if I solve it, it will look not super important later. Or so I would say there is one important direction that I didn't talk about at all. That are the definition of new kind of weeds. This is a very active field in structural graph theory. I have colleagues in Lyon involved in this, like Stéphane Thomasé, Edouard Bonnet, and Rémi Vatrigans are in the team in Lyon. They invented a new notion that is called twin weeds. This is a nice direction. I think more in the line of what I do, I really think it would be needed to have to know more about the structure of even-hole free graph. I believe it is still an important question, even if it is very specialized, because it is very weird that this class that is much simpler than perfect graph doesn't have an algorithm for alpha and chi. It is really a mystery why you have something that is much simpler and you cannot do algorithm. So I think this should be understood in some way. I don't have a magical prediction. No one knows. Before you prove things, you don't know. But it could be that maybe coloring even-hole free graph is in fact NP complete. And this would explain a lot of things. It would explain why I didn't mention this, but for coloring perfect graph, there is no combinatorial algorithm that is known today. This is a famous open question. So proving that it is NP hard for even-hole free graph, it is structurally simpler and it is NP hard. It would, in some sense, prove with quotes, because it's not really a proof, that there is no combinatorial algorithm for a perfect graph. There is a good reason for that. And so I think a full understanding of the structure of even-hole free graph would really shed a light on a lot of open questions that are still in the landscape today.
Okay. Thank you, Professor Nicola.
Okay. Any other questions? Please.
Maybe I would like to ask something.
Okay, Devi, please.
Hello, Nicola.
Hello, Dewi.
Quite well that we didn't meet. Yeah, I actually what Nicola present today, I think that I have heard most of them. So it's I agree that what with Nicolas said and what Professor Eddie said, that this topic is quite difficult, but I found that it's really nice. But maybe for beginner, it will take time to really work on even whole free graphs. So for that reason, today I will not ask about technical things related to even whole free graph. I'm rather interested to look for if you know maybe small problems related to graph decomposition that might be suitable to be worked with undergraduate or master students. Because last year, in the end of last year, I also give a talk on the society that works on combinatorics in Indonesia, that I talked about graph decomposition, and I found that many people interested in applying decomposition technique to solve graph problems on maybe I will not say small simple class of graph, but small, like maybe simpler than even whole free graph, something like that. So what I'm thinking of is to apply decomposition technique to solve graph problems such as variants of graph coloring. In Indonesia, many people work on graph labeling, and there are many variants of it. Maybe you could share your experience, Nicola, when working with some classes of graph, especially when using decomposition technique, how usually we decide how we will decompose the graph such that we can apply it to solve a problem, for example, graph coloring problem. That's my question. Thank you.
Yes, I don't know if I can answer this question now.
It's just general idea, maybe.
It is very general. Yeah, yes. I don't really know. It's hard. Yeah, there is something a bit strange. I don't answer directly your question, but I must say you said that even whole free graph is something which takes time to get used to it. I would say as most fields in research, what is a bit weird with even whole free graph or perfect graph is that the tool, if you read, for instance, the proof of the strong perfect graph theorem, it is a masterpiece in graph theory, but the tools that are used are not very sophisticated. It is a very strange balance of things. You have 150 pages, and I would not be able to, if I don't know, if some colleague in number theory, I ask him, what techniques do you use? A mathematician, he will tell me, oh, we are using probabilistic tools, we are using stochastics, blah, blah, we are using differential equation, geometry, algebraic geometry, etc. If you ask me, what are the tools used to prove the strong perfect graph conjecture, apart from making inductions, only super basic tools are used, but in a super complex way. It is which is a bit disturbing. It is a bit disturbing, but I have no explanation for it. It is like that. And as a result, it takes a lot of time when you study this to see the big picture of what is because you can make very easy stuff in structural graph theory also. I know about chordal graph. You can generate a lot of theorems that are a bit easy, and it is really hard to see the big direction, where to go, etc. So the question you asked, Dewi, is very difficult, and there is not a 2-minute answer to it. I would say that there is something important that I think a good guideline in all this is that when you talk often with people from the field, there are theorems and papers, and there are also stuff that people know and believe. For instance, I give you an example from the talk. It is the star-cut set. The star-cut set, I defined it in the talk, and it is a decomposition, and it is well known that star-cut set do not lead to a polynomial time algorithm for coloring. They are hard to use. So they kind of answer your question, but not in the way you hoped, maybe in the negative way. Here is a decomposition that it is bad. But in fact, I am not aware of a real proof of it. I mean, each time you try to use it, you see it doesn't work. But I am not. I think it's a work for an undergraduate. It should not be complicated to design a class of graph artificially that is decomposable with star-cut set, and it is into very simple stuff like cycles, for instance, and it is NP hard to color the class. You see, this is a simple, and no one does it because it is not. You will not publish this in a super fancy conference because it is something everybody knows. Or be careful, it is something that everybody believes he knows. Because once you don't have maybe there is a surprise. I would say 1% chance that there is a surprise that in fact they are usable. You see, I don't believe this. No one believes this. But I think this is the kind of stuff that no one really investigates because it seems clear. But to my knowledge, no one ever did a formal proof that I have star-cut set and I cannot color. And it might be that you have a simple answer to this, some things that take 3-4 pages, and I think this is a nice way to put a step in this theory, to have stuff that seems to be clear, but no one takes the time to write them. It is a good way to enter in the theory, to have something new, and then you understand things, etc. By the way, your PhD Teori was kind of like that. Remember, we took this class of theta triangle free graph. It was obvious to me that they should have bounded triwids. It was really a big surprise that we found this construction. So there are surprises sometimes, and but it is true that it is hard to identify the good question. I mean, that has a reasonable level of technicality to be solved, and that shed a light on something. And the one I gave you here, I never took the time to do this. And maybe it's interesting.
Thank you, Nicolas. I think I get the point. I get the answer for my question. Actually, I asked this because I found that it's hard to convince people to work on this, but I found that it's interesting to work with the technicalities and stuff, and I'd like to bring it to the students. So that's so I think I agree with the points that you said, and now I find something that may be suitable for students. Like we can just give some class of graphs, like simple one or maybe not very simple one, and try one decomposition technique and let them to play with that. Maybe that's good. Just to know what is structural graph theory. Thank you. That's very nice talk, and I'm very happy to see you in Indonesia.
I hope we can meet again somewhere in France or Indonesia.
Or Indonesia. Okay, thank you, Devi. Okay, any other questions? Okay, Nicolas, this is just a simple question from the outsider. Are there any a connection between structural graph theory with combinatorial design? Can you say something about it?
Combinatorial design are this kind of stuff where you have a kind of a matrix and you want that you have you have 5 stuff in each row and 4 stuff in each column.
Right.
Yes.
Okay.
So I'm not aware of this. I am not aware of this. There might be a link, but I'm not aware of any.
Okay. Okay, so maybe last question I invite, if any. So please, if you have any other questions, last question maybe. Okay, so if no, then thanks again to Professor Nicolas to give an inspiring and interesting talk. Okay, now I go back to Pak Edi. So please, Pak Edi.
Okay, so thanks again, Professor Nicolas, for very exciting and interesting lectures that you've given today in our event. So on behalf of the Faculty of Mathematics and Natural Sciences, we would like to present you some certificate of this seminar, of this webinar, and also some a small token of this. Let me present you.
Okay.
Okay, so this is the certificate of the appreciation.
Okay, thank you.
And also one more. This is our thanks. So this is a caricature made by our student. I hope you.
Yes, that's very nice.
You enjoy this caricature. Okay, so
yes.
I will send you both document by email.
And who is the student? He or she is very talented, no?
He's my undergraduate, undergraduate student. He uses software, not by hands, but he uses software, and but with some programming a little bit. Okay. Okay, so I will send them to you.
Yes, thank you.
By email. Sorry. Yeah. So I think we reached the end of this event. And again, thank you, Professor Nicolas. Hopefully, Professor Nicolas can visit us in Bandung sometime next year. Actually,
so yes. You know, I am head of my lab. I am in a bureaucratic nightmare. I could. Yes, French bureaucracy is much more complex than structural graph theory. And I am involved in it, so I have really little time for research in the past 2 years, and next year it is very difficult for me. I have super little time for research. So it could be that if you send me an invitation, I just cannot come. But this is a position that should end up within something like a year, and then after I will be much more available and very happy to travel.
Okay, hopefully next time. Yeah, if not,
but still
2024.
Yeah, but still, we can discuss 2023. It is not that I say no, but it is complicated. I just wanted to say it is complicated.
Because in next year we are also plan to have international conference. We are holding international conference together with our colleagues in Japan. So this Indonesia-Japan International Conference. And Ibu Hilda, Dr. Hilda Asyatun will chair this conference, and the conference will be held in Bali.
In Bali, so where Dewi is from.
Yeah,
Right.
yeah, that's right. So Bu Hilda, would you mind to explain a little bit about the conference?
Actually, it's not me, it's Nino, Pak Edi.
Yeah, atau Bu Rino, Dr. Rino.
Yeah, it's
Dr. Rino. Dr. Rino is not English, yeah. Okay, so we planned it to have a conference on September.
September
Next September.
2003.
Yeah, 2003. If you have a time, so I will write you.
Okay, thank you very much. Thank you very much.
Just to let you know, if you are possible to come, then would be wonderful. Yeah, to see Bali and also Bandung. And
Yes.
you can also play angklung in performance.
Okay, I would be happy to try it.
Okay, so thank you, and thank you to everybody, yeah, for being here at this event, at this webinar. And I think we close this event.
Thank you very much.
Yeah, bye-bye next year.
Thank you, Nicola.
Thank you.
Bye-bye.
Thank you, Professor Nicola.
Yeah.
Bye-bye from now.